Now, when we know what is vector and how to work with vectors, we can consider geometrical objects and we can describe the points, the sets, using vectors as n-tuples of real numbers and some functions and arithmetic operations between them. So let's have a look at some simple geometrical objects and how to describe them using vectors. So perhaps we can start with a very simple case. Just one line, R. We can describe a point on a line by the coordinate x, just one real number. And this coordinate, the point may be either fixed, constant, or it may move. If it moves, then the coordinate x is some function of some parameter t, and we can think of t as time. And then we can consider the first derivative, this is the velocity, the second derivative, this is the acceleration, and some properties of the function, how x depends on time t, reflect some typical motions in the plane. Say, if the function is increasing, the points move to the right. If the function is decreasing, it moves to the left. If the function is periodic, the point moves up and down, a sort of oscillation. If the function is injective, the point does not return to previous positions. If it is not injective, then it comes back where it was already. But from the geometrical point of view, line is too simple. Okay, let's consider something more interesting. Let's consider plane, R2. Then we have two coordinates. We can call them x and y. And once again, we can have a point here with fixed coordinates x and y. Or we can have x and y changing with time t, with some parameter. If these two functions are complicated, then we get some curve that may look like that. We want the functions to be continuous and perhaps to have derivative. And if the functions are simple, in particular if they are linear, if it looks like, say, 2 plus 3t and something like 1 minus t, that means a constant plus a constant times t, and similarly for y. Then this describes some parametric, this is parametric equation of a straight line. We can describe a line in a plane by several possible mathematical ways, several possibilities. This is the parametric equation of a line. We can call the two coordinates x, y as a vector or point capital X. We can consider these 2 points as a point A, and we can consider these 2 coefficients, 3 and minus 1, as some tangent vector v. And then the parametric equation of a line in a plane, maybe x is a plus the parameter t times the tangent vector v. And here capital X, capital A and v are 2 component vectors, and t is a real parameter. This notation is nice because it remains valid even for higher dimensional cases. If we remove t, it could be done by expressing t from the second equation to get 1 minus y. And if we substitute this t here, we get x is 2 plus 3t. That means plus 3 minus 3y. And then we can write that 3y is equal to 5 minus x. And then y is 5/3 minus 1/3 of x. And this number, minus 1/3, is called slope, and it determines the direction of the line. If the slope is positive, it is an increasing function, it goes up, and if the slope is negative, it goes down. So that was the parametric equation of a line, and this is the slope equation of a line. And the third possibility, the third common way how to describe a line in a plane is the general equation of a line. Namely, first we want to get rid of the, we can write it, we can use this line, and we can write it in the form x plus 3y is equal to 5. Let me write it once again here. X plus 3y is equal to 5. And this is called the general equation of a line in a plane. It's more general than this one because the slope equation does not describe a line that is vertical, that is parallel to the y-axis. While if we have some coefficients and some number here, this way is good even for describing a vertical line. Namely, a line, say the y-axis alone could be described by x is equal to 0. If we write it as ax plus by is some number d, then for the slope equation we want b to be non-zero because we want to express y as a function of x. But exactly for lines that are vertical, b is 0. So this corresponds to the case when a is 1, b is 0, d is 0. So this is a special case of this general equation of a line. These two numbers, a and b, may be again written as a vector, and this is the normal vector to the line. If the line looks like that, then the normal vector is perpendicular or orthogonal to the line. So these are the three ways how to describe a line in a plane. Now let's come to the still more interesting case R3. Once again, if we denote AB as an arrow, the normal, then this line can be written as n dot product capital X, the point xy, is equal to d. Well, we can still use such an equation in R3, n dot x is equal to d, and in R3, n arrow and capital X are triples of real numbers, and d is just one number. In R3, this is the equation of a plane, and in a higher dimensional spaces, this is called hyperplane. Let's consider some particular example. Say if the number vector is 1, 2, 3, and say this u is 5, and capital X is x, y, z, then the general equation of the plane looks like x plus 2y plus 3z is equal to 5. So this is the general equation of a plane in a three-dimensional space. But similarly, as we can describe a line in a plane or in a three-dimensional space, we can use a similar form to describe a plane in a three-dimensional space. If we use this is still a line in even a higher dimensional space. And to describe a plane, we start with a point A, and then we can move away from this point in the direction of the vector v. But in a plane, we have more than one direction to move away. And this can be described by another vector, say s times w. Then v and w are two directional or tangent vectors in the plane, and A is a point of the plane, and t and s are real parameters. Now, sometimes we want to convert from the parametric equation of a plane to the general equation of the plane. So it would be nice to have some relation between the tangent vectors v and w of the plane and the normal vector of the plane. And if you consider a plane like that, and if you consider two directional vectors, then the normal vector is perpendicular to the plane, and so it is perpendicular to any vector in the plane. So if we have two vectors in the plane and we want to find a perpendicular vector, we can consider the cross product, the vector product. So one possible normal might be v cross product w, because we know that the cross product is perpendicular to the two vectors. Okay, let's consider some example. Let's consider the parametric equation of the plane in the form x is 1 plus t minus s, y is t, and z is 2 plus s. Then we can see that the point A is 1, 0, 2. The first tangent vector v is the vector of the coefficients of the parameter t, which is 1, 1, 0, and w is the vector of the coefficients at s, minus 1, 0, 1. And then we can find the normal vector as the cross product v cross w, which is the determinant I, j, k. Now on the second row we write the coordinates of the first vector, 1, 1, 0, and on the third row we write the second vector, minus 1, 0, 1. The first coordinate is 1, the second coordinate is minus 1, and the third coordinate is 1. It's a good idea to check this result. It should be perpendicular to v. Is it 1 minus 1 plus 0 is indeed 0, the scalar product, and it should be perpendicular to w as well. Minus 1, 0, plus 1, yes, the scalar product is again 0, so they are indeed orthogonal, perpendicular. When we have the normal vector, we can write the general equation here. But we don't know the parameter d, the coefficient d. But if we know that some point A is in the plane, then it must satisfy this equation as well. So d can be just n times A. So we prepare the scalar product n dot A. Here we have n, 1 minus 1, 1. And here we have A, 1, 0, 2. So the scalar product is 1 plus 0 plus 2 is 3. Well, and at this point we can write the general equation of this plane, namely 1 times x minus 1 times y plus 1 times z is equal to 3. In this way, we can convert the parametric equations of a plane into the general equation of the plane.